A very good morning, good afternoon and good evening to all the participants, the candidates and my dear students. Uh, welcome to this NPTEL MOOC course, title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as usual, as I start, the three main topics for this whole course of 60 lectures, 30 hours, the main three topics are forecasting, second one is regression, third one is time series. And we are going to the in-depth analysis of regression models. This is week number 7 and this is lecture number 33. The coverage would be continuation of the multiple linear regression discussion, examples for MLR, and before I come back to the MLR, I would like to discuss few more practical examples of simple linear regression models. So, obviously, the continuity, I thought that yes, we have discussed some theoretical examples trying to find out the beta naught value, beta 1 value, that is with their respective estimates, and then find out what is the best fit line, how the error looks like, what we are trying to do, that we are trying to basically minimize the sum of the squares of the errors. That would also be brought into the picture before we go into the in-depth analysis of MLR. And as I always mention as I am going forward with the classes, that the coverage as mentioned, depending on what is the speed of the lecture, whether I need to go into depth, when you see the main slides, basically please follow that and with the lecture. So, that would make much better sense. So, what I am talking about, what are the examples I am showing would exactly be reflected in the actual PPT slides when you get them. Now, if you remember in the last class, I spent a lot of time trying to analyze that there are two main tasks. Number one, to find out the estimate of beta, and number two, find out that if that is an estimate, whether in the long run the expected value of that beta hat, estimate beta means that beta hat which you want to find out, in the long run whether the expected value of beta hat is equal to beta. Because if that is true, then the concept of unbiasedness would hold, which means that if I keep picking up observations and I find out beta hats, when I am talking about beta hat, I mean that set of vectors. Vector in the sense I am finding out beta naught hat, beta 1 hat, beta 2 hat, beta 3 hat till beta k hat, considering k number of independent variables. Based on that, I need to find out that expected value of beta naught hat is equal to beta, expected value of beta 1 hat is equal to beta 1, and so on and so forth till the last value of beta, which is expected value of beta k hat is equal to beta k. So, that was proved. Number 2, we also wanted to find out the variance. Now, variance of those set of beta hats. Why? Because the important fact is that if you remember from DADM1, which is Data Analysis and Decision Making 1 course, which is also there in the NPTEL MOOC series, which I have taught and where the lectures are uploaded, the concept of consistency important in the sense that the variability for that estimate for which we are sure it is unbiased, it should also have the least variance. So, that means we will be able to get the minimum variance unbiased estimate. And we have already found out that considering the fact that the x values are independent of each other, that means the independent variables are independent of each other, that is point 1. Point number 2, the errors do not affect the independent values, and independent values or variables do not have any effect on variance on the error. Hence, the covariance structure between the x with themselves would be basically mean that you only have the variance of each x, point 1. Point number 2 is that you do not have the covariance between xi and xj, where I is equal to and j is equal to 1 to k. K is basically the number of independent variables. And number 3 is that covariance between the error and any x is 0, and also the fact of concept of the homoscedasticity and the concept on non-autocorrelation were two important facts which I have highlighted time and again in the discussion with simple and intuitive detailed graphs with definitions also. Because why I am highlighting this point of homoscedasticity, heteroscedasticity, autocorrelation, non-autocorrelation is the fact that we will be revisiting this again in the time series concept. Thus, once we have the covariance of beta hat, the covariance of the beta hat would be given by the formula which you see in front of you in the slide. This one, sigma square, we are aware, and this matrix which is X transpose X, which you already have, we know it will be of size. So, X is basically of size n cross k, transpose of that is equal to size of k cross n. So, when you multiply k cross n into n cross k, you have the matrix which is k cross k, and inverse of that is also of k cross k. That means, as we know that there are basically k number of betas, hence the covariance of beta, the covariance variance structure of beta which you have would be a k cos k matrix. The diagonal elements are the variances of beta, which is very intuitive, because if I take the principal diagonal, the first one would basically be the covariance of beta 1, which is basically with itself, which is the variance of beta 1. The 2 comma 2 element would be the covariance of beta 2 with itself, which is variance of beta 2, and k comma k element would basically be the covariance of beta k with itself, which is the variance of beta k. And the off diagonal element would basically be the covariance of the ith and the jth beta. The off diagonal elements are basically the covariance between, say for example, beta hat j1 and beta hat j2, where j1 and j2, if they are equal, it is the principal diagonal. If they are not equal, they are the off diagonal elements, and it is from 1 to k. Few properties important without proofs. Beta hat is the minimum variance linear unbiased estimator of beta, whether x is stochastic or non-stochastic. This will always hold true. Hence, beta hat is the best estimator. And if I multiply that beta hat with some weight, so this W transpose which you see is the weight, is the minimum variance linear unbiased estimator of weight into beta. That means, weight do not change. So, I only need to replace beta with this corresponding estimate, which is beta hat, where WT, where W turn transpose is any vector of constant, whether x is stochastic or non-stochastic. So, for the weighted case also same estimate, and for the case when you have the simple concept of beta, again the same estimate. This is the beta hat which we have found out already by minimizing the sum of the squares of the errors and differentiating that sum of the squares of the errors partially with respect to beta at each step. And then we get k number of equations, k unknowns, solve them and get the beta hat. We know that the expected value of the error terms is sigma square. That is the sigma square what we had in the last slide, sigma square, and in the bracket x transpose x, that inverse. So, sigma square is basically the variance of the error, and this is also has been mentioned time and again when we considered each error is normally distributed with 0 mean and sigma square as the variance. And the concept of non-autocorrelation would obviously immediately give you the idea that the errors are independent of each other, that it is not time dependent, and the concept has been mentioned time and again from my side. We also know that this, that was epsilon, this is EI is the estimate of error and is basically the corresponding sample counterpart. Like you had beta for the population, you have beta hat. Similarly, you have the concept of epsilon as the actual error in the population and its counterpart is EI. The least square residuals. So, this is the residuals which we have. I will highlight it once again. So, E is the residual and some of the residuals should also be 0 as per the concept. The least square residuals E is given by the fact that we are able to find out its expected value of the square of the residuals. In the same way as I am trying to find out the sum of the square of the errors, in the same way we are trying to find out the sum of the squares of the residuals. Residuals are denoted by E, the alphabet E in English, and this error is denoted by epsilon, the Greek alphabet. Both are small. So, when we prove it, again as I said, I am not going to go to the details of the proof. These are just given for your interest. Somebody is interested to go into depth. So, E transpose M into E is a 1 by 1 matrix depending on the dimension, and thus if we use TR is basically the trace. So, if we use the concept of trace, the actual value of the residuals expected value of E square would be this, and this is important. So, if you see, the formula is n minus k into sigma square. Sigma square was the variance of the error, while the variance of the residuals is sigma square multiplied by a factor n minus k. N is the number of observations, k is basically number of independent variables, and we will come to the concept of, if I remember, I did mention of ANOVA, which I will actually come into when the multiple linear regression models would be discussed in details. So, degrees of freedom and all these things would be considered, and there in the in one concept, if you remember, I mentioned R square and adjusted as R square, there this n minus k would be relevant. Now, as we know that if I need to find out the expected value of the residuals in order to prove whether it is unbiased or biased, then obviously in that case n minus k is there. So, having n minus k would mean, in the numerator if n minus k is there, it would mean that it is biased. So, in order to make it unbiased, what we do is that we I will use a different color, green. We divide the residual square by n minus k, that we denote by s square. I will use a different color. So, s square is basically the ratio of residual squares divided by n minus k, and if I have that, we get basically in the term on the right hand side, we get it, which is the case where if I find out the expected value of s square, it is unbiased because we will get sigma square. Now, the question you may all be asking is that, did we learn something here from previous concept? I just want to step back and tell that if you have done DADM 1, data analysis and decision making 1, there the concept when the population parameter of, say for example, the mean value was not known, we utilized the sample variance to find out the best estimate for the population variance. There the concept was, if you remember, I am only going into the basic formula, I will use the violet color. The formula was given by n minus 1 summation of xi minus x bar whole square, and this x bar is basically the sample mean for x, and there is only one x, hence k is 1, and if you see this formula, I will use the red color, this n minus k, when k is 1, it becomes basically n minus 1. So, this we have already dealt with. If somebody, again I am saying somebody has done DADM 1, or you are aware of the basic concepts from statistics. So, actually again the residual is biased. So, you basically find out the square of the residuals, divide by n minus k and get s square, which is unbiased. So, the unbiased estimate of the errors is not residual, but s. Actually, I should use the word these unbiased estimate for sigma square is not residual square, it is S square, because the residual square is biased. So, we know finally that the error term which we have been talking about, we did discuss, the error term is given by normal with 0 mean and sigma square. I is an identity, that is the variance, and beta is basically distributed normal, beta hat with beta as the best estimate we have already proved. I am putting a green tick mark, and the corresponding covariance structure where I am putting a blue tick mark is given by this, again we have discussed. So, which definitely implies that here when we get it, beta hat each element would basically have its corresponding estimate given by its population parameter, estimate for the population parameter we are getting from the sample, and the variance would be given by the principal diagonal, because it is given as j comma j, that means all are equal, that means 1 comma 1, 2 comma 2 till k comma k. Now, as I mentioned, we will now discuss some actual practical examples of first simple linear regression, then multiple linear regression, and in the similar way we will also discuss some theoretical examples of multiple linear regression. So, if people are aware, in finance we use the capital asset pricing model, so which is CAPM, and the actual formula for which is given by this, which is actually a sort of simple linear regression. So, this can be termed as y, and on the right hand side you basically this term can be denoted as x, and this term is basically the beta. So, here what is RI? RI, capital RI is the return of the financial asset ith one, and RF is basically the risk free interest rate. Risk free interest rate considered from the RBI side, the T91 day bills, which is treasury bills for 91 days. And RM is basically the market return, market like NSE 50, BSE 30, whatever it is. And also again on the right hand side you have RF and epsilon. Epsilon is basically the error, and they are given by suffix I is basically the number of readings. Now, we assume as per the concept, the overall error as per the concept of multiple linear regression, simple linear regression has a mean value of 0 and variance as sigma square or 1, we will consider as sigma square, which is constant. That means, there is no autocorrelation concept, and the concept of homoscedasticity is also holding true, even though for financial data point that may not be true, highly unlikely that it would hold true. Now, for these what I am formula I am writing, this again I am saying they are just for your interest, not directly related to the course. So, any concept related to that would not be included in the final question paper, but maybe as you read the slides, see the videos, some questions may be there related for only for the assignment sake. So, if I have basically the prices, and I will use a different color, prices of the stocks. So, I have P1, P2, so where the suffix relates to the day, and in price you have basically the opening price, the maximum price, the minimum price, the closing price. So, we will take the closing price which reflects all the trading, all the information which has been done throughout the day. So, basically if I use the prices based on the fact that capital R would be calculated by the concept of P2 by P1. While if we use the concept of small r, I am using the green color, that will be given by P2 minus P1 by P1, and based on that I utilize this return. So, this capital R and small r is not given here, if we can replace capital R by small r and do the same calculations, but in actually the return small r, I will use a different color because the formula is different, is actually ln. This is the natural log, logarithmic Neperian log, which will be p2 by p1. So, we will get the small r value. So, we can replace that here also. Now, I just deviated because I wanted to mention what is capital R, small r, people if they are not aware. Now, having said that the error terms is normally distributed with 0 mean and some standard deviation, if I find out the expected value, then the term on the right hand side, the last term which is the error, expected value will be 0. So, hence the so called best fit line which you am seeing there in the simple linear regression models would be given by this. So, it means that if I consider R I minus R f as y and R bar, so R bar sorry average values, which is R bar I minus R f we consider as fixed, even though in practical sense it may not be, and in the right hand side you have beta I in the bracket R bar m minus R f. So, R bar m is basically the mean return on the market, R bar I is basically the mean return of that particular stock. So, this equation is almost like y is equal to mx. C concept is not there. So, we can bring the concept of C accordingly. If I have this equation, I will use say for example, the orange. So, from the green one I can have R I is equal to beta I into R bar I is equal to beta I into R bar m, and the terms which we already had. So, R f will go to the right hand side. So, it becomes minus R f, and there is already term which is there, which is beta I into R f. So, this term can be considered as C. So, you will have y, so equal to mx and C. So, C this, mx is equal to this, y is equal to this. So, we have replaced, rather than y is equal to mx, we have made it y is equal to mx plus C. So, market index portfolio is basically the fund that contains shares of every stock, which is M in proportion to the stock representations, and asset weight is defined as proportion to the portfolio capital which is allocated to the asset. So, we need to basically find out what is the proportion, and based on that we will try to find out as given by the returns what is the rate of change of that particular stock price or returns with the market, because market is being considered as independent variable and the return for that particular stock as the dependent variable. So, weight of the asset is the market portfolio, which is equal to the proportion of that asset's total value in the capital value to the total market. So, total amount invested divided by the total amount invested in that particular stock divided by the total amount of money invested. So, say for example, there are 5 stocks, I have total amount of 100 rupees, and if I invest say for example 20 amount rupees in the first stock, so the total weightage would be in monetary terms would be 20 by 100. So, which is weight. So, if I basically invest in the next stock is basically, if I had 5, so I have already invested 20. So, the rest 80 I divided in the other 4 in the same proportion, then obviously they are also 20. So, the equal proportions of amount of money is invested in all the stocks starting from 1 to 5, which is basically 20%. In case say for example, if I invest, if I have basically 5 stocks and if I invest in one the amount of 50% so of 100, which is 50 by 100. So, the rest 50 of 100, which is 50 by 100 will be divided say for example, equally in the rest of the 4 stocks. If I have 3 stocks and I am investing equal proportions of amount of money in all the 3 stocks. So, it will be 1/3, 1/3, 1/3 in each of them. Now, the capital asset pricing line, which we will try to find, shows the relationship between the expected rate of return and the risk. Thus, as the risk increases, so does the expected return. Mathematically, we can define this as linear regression given by the model this. So, here what you have is R p bar Forget about the efficient concept, is basically the portfolio. And if you consider on the right hand side, you have RF, which is the risk free interest rate, and the ratio of R bar M minus RF by sigma M would basically multiplied by sigma of the efficient portfolio. So, if I find this equation and then it will be basically given by a straight line. The slope of this capital pricing line is basically the price of the risk, because price, if you see the, I will use the blue color or the violet. So, this means price of the risk means in the numerator you have the difference of the return RM and RF. So, if the risk free return is, say for example 5% and the market return is 10%. So, I am getting, if I invest in the market, I am getting extra 5%, 10 minus 5. So, that is so called positive thing which I am gaining. And if the standard deviation is, say for example 2, so that means it will give you for 2 units of risk I am getting 5, hence it is known as a concept of price of risk. So, per unit of risk, what is the price? So, this is the capital market line or pricing line, and if I plot it, consider this is the coordinate point where it touches the and that is the intercept. So, obviously, in that point the value of the return will be given by RF, and obviously, the value of the risk is 0, because it is along the y axis. So, obviously, this would mean RF means the value of return, which is the risk free interest rate, and any point which you have would be based on the tan of that angle. Tan of the angle would be given by the slope. The capital market line or the pricing line relates the expected rate of return of an efficient portfolio to its standard deviation. Remember, it does not show how the expected rate of return of an individual asset is related to its corresponding risk. So, if the market portfolio M is efficient, then the expected return of any efficient portfolio is given by this formula. Now, why I am discussing that? Because the point of simple linear regression always comes into the picture. So, if the market portfolio M is efficient, then the expected return of any efficient portfolio is given by R bar P. R bar P is basically for the portfolio, RF is basically the risk free interest rate, and on the right hand side is exactly the same equation you have considered. It is basically beta P, which is beta I what we are considering, R bar M minus RF, which is the difference between the market minus the risk free interest rate. And once I expand it, exactly this equation I am getting, which is exactly similar to the simple linear regression model, which we will consider very soon. With this, I will stop this class and continue more discussions about simple linear regression model further on. Thank you very much and have a nice day.